In our previous lessons, we dealt with the knowledge area matter and materials. Now we're going to look at the knowledge area chemical change. So, at a very basic level, we find that there is matter, interaction, and change. Now we know that chemical reactions can give off energy as well as absorb energy. We also know that physical changes can give off energy as well as absorb energy. But we know that energy is key to understanding of chemical phenomena. But what is this thing called energy? What is energy? You'll be surprised to know that there's still much deliberation as to what energy is. Normally, at our level, we tend to say energy is the ability to do work, but that's a very simplistic definition. To get a technical answer, we have to look at the theory of relativity. Einstein changed our notion of matter and energy. But for our purposes, let's look at energy, and there are essentially three forms. We have kinetic energy, we have potential energy, and we have electromagnetic energy when we're dealing with chemical reactions. Kinetic energy we know is equal to half mv squared, and potential energy or gravitational potential energy is equal to mgh. Kinetic energy, which is equal to half mv squared, that equation is fine. It applies approximately in a classical sense, but we cannot use that equation once the particle is moving at the speed of light. But that's beyond the scope of the course. Now, when dealing with energy, it is important to define the system. And the system can be chosen as the reacting particles in a beaker, or everything outside the boundary of the particles is the surrounding. So in a chemical reaction, when bonds are formed, energy is released by the system. And when bonds are broken, energy is absorbed. That's important to remember. Whenever bonds are formed, energy is released, and when bonds are broken between atoms, energy is absorbed by the system. Let's look at the properties of matter. A property is essentially a variable of state. It allows us to recognize a substance. It is a characteristic of the substance, and it allows us to distinguish substances. I've got a few properties of various substances, and these I got from databases, international databases, which give you the properties of these substances. Now let's look at sodium chloride. Sodium chloride, you know, we have dealt with it, and we know it's an ionic solid, and it contains Na plus and Cl minus ions, which extend throughout the entire framework of the solid. Let's look at its appearance. It says appearance is a colorless cubic crystal. Odor is a property. It's odorless. Let's look at the density. The density is about 2.17 grams per cubic centimeter. And you can see its melting point is quite high, right? it's about 1073 kelvins, which is high, and we attributed that towards the very strong ionic bonds between the positive and negative ions. And look at what the boiling point is. The boiling point is 1465 degrees. Look at the solubility. The solubility is 360 grams per liter. Right? So if salt is dissolved in water, 360 grams per liter of that solute get dissolved. 360 grams of the NaCl gets dissolved in a liter of water. Solubility in ammonia, it also gives you a property there, which is 21.5 grams. And it is also soluble in methanol. Right, and then we have the refractive index. Refractive index is a concept we'll be doing in grade 11. It gives you an indicative measure of the bending of a ray of light when moving from air into the sample of which you want to determine the refractive index. Let's go to the next one. Silicon dioxide, we did that as well, gives you an indication of its properties. And if you look at the density of it, it's the density here, right, is 2.196 grams per cubic centimeter. It also has a boiling point. And also the refractive index is given to you here. Let's look at water. Water, we know, is molar mass. It has been given to various number of significant figures, and it's 18.01528 grams per mole. And we know it's a colorless liquid. Odor, none. Look at the density of water. It gives you the density at 0 degrees, at 25 degrees. Melting point, we know that you did at the beginning of the year when you dealt with the cooling curve and heating curve of water. Here's the boiling point. And then its solubility in organic substances. Right? Let's look at NH3. There's a molar mass of 17.031 grams per mole. Its odor is pungent. Let's look at its melting point. Melting point is minus 77.73 degrees Celsius. And boiling point at minus 33.34 degrees Celsius, which indicates to you that it starts melting at 77.73 degrees Celsius. I mean, below that temperature, it's a solid. It starts boiling at minus 33 degrees about 33 degrees Celsius, and between the melting and boiling point it's in a liquid state, and after a temperature of minus 33.34 degrees, then it exists as a gas. That is why at room temperature ammonia is a gas. Let's look at sugar or sucrose. There we've got a molar mass. We have its density. Look at the solubility of sugar. 909 grams per liter. Well, let's go back and see what was the solubility of sodium chloride in water. That's salt. There it's 360 grams per liter. So sugar is much more soluble in water than sodium chloride. Now let's look at the properties of matter. We look at the physical properties and the chemical properties. Physical properties can be measured without changing the composition of the substance. Properties like color, density, melting point, and hardness, these can be measured without changing the composition of the substance. Chemical properties, on the other hand, they may change or react to form other substances. One such property is flammability. It is the ability of the substance to burn in the presence of oxygen. And when it does so, it forms another substance. Also, physical properties of materials can be categorized into intensive properties or extensive, according to how the property changes when the extent or the amount of substance changes. Now let's look at these two properties. Intensive property. The magnitude of the property is independent of the size and the amount. I will illustrate that. Intensive property is a bulk. It is a bulk property, meaning that it is a local physical property of a system. Now let's look at this. If we look at temperature, and temperature is regarded to be an intensive property. So let's say, for instance, I have water in here. These are the water particles. And let's say the temperature is 20 degrees Celsius. And let's say I have another beaker and I take some water out here, right, and put it in there. We find that the temperature of this sample would still be 20 degrees as well. So let's say A was 20 degrees and B was 20 degree, is 20 degrees. So we see that temperature is an intensive property, doesn't depend on the amount of substance or the mass that is used. The reason being also, temperature is, we know, is directly proportional to the average kinetic energy of the molecules. So if you look at, maybe let's assume we have beaker A and beaker B. Here we find that both have the same temperature, and from there we infer that both have the average, same average kinetic energies. Right. Then we look at the idea of refractive index. Refractive index is also intensive property. And like I said, you're going to be dealing with refractive index in grade 11, but I will just illustrate it slightly here, that let's say for instance we have a sample here. What it really does is, let's say there's a normal. A normal is a line perpendicular to that surface, and let's say I have light striking the surface, incident light, and then we have an angle between the normal and the incident light, and let's call it theta 1, and let's say when it moves from A into glass, it refracts. That means it bends, and there it has theta 2. That's the angle between the normal and the refracted ray. So it moves from A, let's say it goes into glass. So the extent to which the ray bends in the glass gives us an indication of the refractive index of the glass. Now, if, for instance, we have the same glass there, and we allow light to strike it, the refractive, or the extent to which it bends would be the same. So the angle between the normal and the refracted ray doesn't change if the size of the substance changes. Why refractive index is a intensive property. Alright, then we go to, say, density. Right? So let's say for instance we have, let's say I have water in here, and let's say for instance I have 18 cubic centimeters of water, and we know that the mass of it is approximately 18 grams. Let's say I take another cylinder and I pour half of that water in this cylinder here, and we find that the volume is 9 cubic centimeters, and the mass would be 9 grams. Now we know that density is equal to mass upon volume, which means it's 18 cubic centimeters divided by, sorry about that, it's 18 grams upon 18 cubic centimeters, which means it is about 1 gram per centimeter cube. That's the density of the substance. If we look at this one here, also we got density is equal to mass upon volume, which means it's 9 grams upon 9 cubic centimeters is equal to 1 gram per centimeter cube. So the density is an intensive property. Obviously, I mean, you can see the mass of the sample has changed, the volume has changed, but the density, which is a measure of mass per unit volume, is a constant. And then we also have hardness of an object. That is also an intensive quantity. Hardness is like the measure of the flexibility of its bending capabilities, and that is also an intensive quantity. I won't go into the equation for that system. Now let's look at extensive property. In an extensive property is additive for subsystems, and the magnitude increases or decreases as they grow larger or smaller, right? So the magnitude increases or decreases. Example of those are masses. I mean, if you have an object with a certain mass, and if you take half that mass, and if you take half that mass, you'll find that the mass changes, right? But let's say, for instance, if I had half a mass here of that, so the mass changes. But if let's assume this was a copper rod, and I had a copper rod with a certain mass, and then I took half the mass of the copper rod. So the mass is an extensive property that changes, but its density does not change, because density is an intensive property. And then we also have like two categories. Sometimes these two categories are not exhaustive. What do I mean by that? They neither exclusively intensive nor extensive. Let's take, for instance, electrical resistance. We know that if I have, let's say, for instance, a resistor there, and it has a certain resistance, which could be 2 ohms, and I connect it to another one with the same resistance, 2 ohms, then we know the total resistance is 4 ohms. So the extent or the size increase and the resistance increase. But there are situations where you can take that and connect it in parallel, where you have that as 2 ohms and that as 2 ohms, and then the total resistance of that system decreases. So it depends how it's connected. Right, now let's look at physical change. A substance changes its physical appearance but not its composition. Okay? Appearance but not its composition. That's how we're looking at it. And then a chemical change is that the substance is transformed chemically into a different substance. So if it's a different substance, that means it has different properties. Let's look at a description at a let's look at this description here. Essentially, when there's a physical change, we have a rearrangement of molecules. Molecules separate. There's a disordering of molecules. There's energy changes and the conservation of molecules apply. Let's look at this here now. We have, for instance, we have a solid changing to a liquid and then changing to a gas. And the other way around, when you got a gas, it condenses, it forms a liquid, and the liquid freezes and it forms a solid. Alright, now let's just look at this conversion from solid to liquid to gas. And we did the kinetic theory of matter, right, at the beginning of the year, and we know that if we had, for instance, if we have, say, a solid, so say we have a solid, and we know in a solid we have a regular pattern, so that's our solid. And then we have our liquid, where there's more random distribution. That's our liquid. And then we have our gas. Our gas. So if we have H2O as our solid, and it changes to H2O, the liquid, to the, let's just do this again. Say if I change the solid becoming the liquid, we know that what happens during that process, it takes in energy. And then we say, if you look at the water as our system taking energy from outside and becoming a liquid, we say that process is endothermic, right? We say the process is endothermic. If we look at it the other way around, and we have H2O liquid, which then becomes H2O solid, this process gives off energy. And we say that it is exothermic. It gives off energy which goes into the surroundings, and we have evidence of this. I mean, you know, you have a freezer at home. If you put liquid into the freezer, you find, and if you go and feel behind a fridge or a freezer, it's always warm because energy is given off to the surroundings. And then also, to change a solid to a liquid, it takes in energy, how much energy does it take. Roughly, if you have about an 18 cubic centimeters of liquid, to change it from solid to liquid takes in about 6 kilojoules of energy, right? And you know energy is measured in joules. Let's look at another physical change here, a mixture of elements, iron and of iron and sulfur. Here we have the element iron and we have sulfur, and they are mixed, right? So iron has its own properties and sulfur has its own properties, right? Iron we know is a metallic solid, and sulfur we know is a molecular solid, it's a non-metal. And when the two are mixed here, we find that the sulfur and the iron filings, they retain their properties. And when you have a magnet there, it still pulls out the iron filings from that mixture. Let's look at now the allotropes of carbon. Here we have carbon, and these are the different allotropes of carbon. We know we did graphite and diamond, right? We also have fullerenes, right? Diamond and graphite are regarded as network covalent solids, but fullerene is regarded as a molecular solid. Since these molecules are discrete entities within the molecular solid. And then we also have this nanotubes, which currently there's a lot of research about carbon nanotubes and how it can be used in electrical systems and in medicine as well. Now the thing is, if we look at, say for instance, graphite and diamond, would a change from diamond to graphite be like a physical change or a chemical change? Now there isn't total consensus about this. We can say, well, the particles have rearranged, so it looks like as if it's a physical change. But if we look at it from the point of view that we have in diamond 4 carbon atoms bonded, one carbon atom bonded to 4 other carbon atoms, whereas in graphite you find that it's 1 carbon atom bonded to 3 others. So the bonds actually change when the one is converted to the other, and we regard that as being a chemical change. But it's contentious. There could be arguments made for it to be allotropic changes are regarded in certain cases as physical changes and in other cases as chemical changes. Let's look at a description of a chemical change. Right, we're going to look at hydrogen peroxide, and then we're going to look at the electrolysis of water. So decomposition there, we're going to look at the electrolysis of water and the energy involved there. So we also have conservation of atoms and mass in a chemical change and non-conservation of molecules. But again, we got in a chemical reaction, when bonds are formed, energy is released, and when bonds are broken, energy is absorbed by the system, and the surroundings loses that energy depending on what we regard as our surroundings. Here we got the electrolysis of water. What happens in this case is you've got water and you've got a battery, and this battery here has a potential difference, and because of that it can supply energy to the water, and what it then does, it breaks up the water molecule into oxygen and hydrogen. There are other species as well in the system, like you may get hydroxyl ions, and you'll get H plus ions, but I'm looking at the overall reaction, and you can see that once water becomes electrolyzed, it means if you use electricity, you can separate these respective elements. And you will also note that if you look at oxygen and the volume of oxygen here and the volume of hydrogen collected is twice as compared to the volume of oxygen. Here, let's look at the molecular representation of it. It means from this we see that if I look at H2O, that means here we've got our hydrogen and our hydrogen there. This is a specific substance. It's water. It has its own properties. We saw what its boiling point is. We saw what its melting point is. Here, in a chemical reaction, we get a completely different substance. Hydrogen is a completely different substance to water. Oxygen also, it's a different substance. Oxygen has its own properties and hydrogen has its own properties. But if you look even at this equation I illustrated, look at that. We got two hydrogen molecules and one O2, and I'm trying to relate it to the volumes we have here. Now let's look at the property. We got oxygen gas, different property to water. Look at what its boiling point is. What its density is. Right? Now let's go to the decomposition of hydrogen peroxide. Your hydrogen peroxide, the formula for it is H2O2, we know. See, I mean, it just got one extra oxygen and it's a completely new substance. And when that decomposes, we get water and we get oxygen. Right? And water has its own properties and oxygen has its own properties. Right? These are the space filling models that we have dealt with already. Now let's look at a ball and stick model. Ball and stick model gives you a bit more information in the sense that when you got H2O, right, we find that when it decomposes, we get H2O and O2. But the point I want to illustrate, remember there's a bond between hydrogen and oxygen. There's a bond. There's a bond. These are bonds. So when this decomposes, these bonds are broken, right? And when the bonds are broken, energy is absorbed for breaking those bonds. But in the products, what happens? Bonds are being formed. And when bonds are being formed, here in oxygen, it's actually a double bond that is formed between the oxygen atoms. The stronger the bonds between atoms, the more energy it releases, right? So what happens if we look at the energy considerations of this particular system? We need to look at whether the bonds in the products are stronger overall than the bonds in the reactants. And if that is so, we find that energy gets released from the system. Let's look at ozone. Just coming back to this um, decomposition of H2O into O2. I could have said, but how do you know it is O2? Why isn't it O3? Right, why isn't it O3? We're saying it's O2. There's a possibility it could have given us O3. Yes, it's possible, but we need to do an experiment in order to determine whether it's O3 or O2. And we know what the property of O2 is. Let's look at the property of O3. This tells you what its odor, it's pungent, it gives you an indication of the melting point, it gives you an indication of the boiling point, and it also gives you an indication of the solubility in water, and oxygen has its own solubility as well. So there are many ways in which we can determine whether it is O2 or O3. We also know that oxygen, if we put a flame, the flame ignites even further because oxygen supports combustion. Let's look at a ball and stick model for ammonia. Here in this case again, we got N2 plus H2 reacts to give us NH3. N2 has its own properties, H2 has its own properties, ammonia has its own properties. When nitrogen reacts with hydrogen, we find that bonds are broken. Bonds broken here. Bonds broken. Even there it's broken, and then it forms. So when bonds are forming, it releases energy, and when the net result of the reactants and the products, if the net result in terms of energy is released and the reaction is exothermic, if the net result is energy is absorbed by the reacting system, then it's an endothermic reaction. Let's look at iron reacting with sulfur to form iron sulphide. Here we got iron. That's iron, and we know what properties. It has metallic properties and is attracted by a magnet, right? Earlier I showed you when the two are mixed, but here in this case you find that the sample is heated, and when the sample is heated you get a completely new substance, and that is iron sulphide. That means you're getting Fe plus S gives you FeS. Right, that gives you iron sulphide. And we know iron sulphide is a ionic substance. We know iron is a metallic substance, and sulfur is a molecular substance. But in any event, like sulfur normally exists as instead of a single atom, it exists as a molecule that has 8 atoms. So it's like Fe plus S8, right? Sulfur doesn't exist as sulfur. It's like when we have our diatomic molecules, they exist as either Cl2, Br2, I2, and then this gives us FeS, which means, and that would give us 8, and then that would give us 8. Right, it means, so we've got the right way of writing that would be like 8Fe plus S8 molecules, and then that gives us the iron sulfide. Now let's look at the properties of iron sulfide here. Let's see, density, that it says it's a gray lumps, sometimes lumps. Solubility in water. Now FeS is a ionic substance, but it's insoluble in water. Most ionic substances are soluble in water, but iron sulfide is not. But it is soluble in acids. Right, now this here is not examinable, but I just thought let me just show you. You've got this NFPA codes. That's the National Fire Protection Association. They normally use like a diamond, and they give numbers 1, 2, 3, 4, 5, like that, and it's color coded. This is useful for people that want to prevent fires, or if there's a fire, what they need to use in order to put that fire off. Yeah, it just gives you, let's say for instance, blue, that tells you if it's 0, it's normal, and if it's 4, it's deadly. Red diamond, fire hazard, tells you if it's when the temperature is below a certain degrees Fahrenheit, then it can ignite, because it gives you the flash point at what temperature it ignites. And then the yellow diamond gives you an indication of the reactivity here. So this gives you an idea. So if you see maybe a van, or these trucks on the road with this diamond, the numbers give an indication of its reactivity and flammability. There's other nomenclatures that are also used, but I've just shown you this. Let's look at the exercise now. Classify the following as chemical or physical properties. Objects made of silver become tarnished. Now, when they say it becomes tarnished, what we mean is that it reacts with oxygen. So it's like saying Ag plus O2, it forms a new substance, gives us Hg2O. So if you look at this, you find that you have that. Now that would be then 4. Right? So we know that we're getting silver oxide, which is a completely new substance. Right? And when silver material is tarnished, you can't just use physical means to get rid of this oxygen here. You have to use another chemical that allows us to remove that oxygen and get our silver back. The red color of rubies is due to the presence of chromium ion. Yes, we can measure that without changing the substance, and that would be a physical property. The boiling of ethanol is also a physical property. Now, 2, a chemist investigates the following properties of acetone, which are physical properties and which are chemical properties. Again, we know melting point is a physical property. Boiling point is a physical property. And flammability is a chemical property because how it reacts with another substance, and it forms a new substance altogether. So, for instance, you got carbon combining with oxygen give you carbon dioxide, and that has completely different properties. Now, state whether the following are intensive or extensive properties. Temperature, we know, is an intensive property, right? It's an intensive property. Remember, when I spoke earlier, temperature is an intensive property, but the amount of thermal energy within the sample is not, right? That would depend on the mass. The color of nickel chloride is also intensive. It doesn't depend on the amount of substance. The amount of energy upon burning. Now, the amount of energy upon burning, I mean, the more petrol burns, the more energy is used. So that could be extensive. Right. But if we're looking at how much energy is released by burning 1 liter of petrol, that would be intensive. Cost of petrol, again, yes, if you're buying a lot of petrol and the more you buy, the more you pay, that would be extensive property. But if you're looking at the cost of petrol per liter, that would be an intensive property. Pressure, you know, pressure is equal to force per unit area, and pressure is regarded as an intensive property. You'll be doing gas laws when you get to grade 11. Hardness is also an intensive property. And then density is an intensive property. I illustrated that. Corrosion of aluminium, is it a chemical process or a physical process? That's a chemical process. So it's like Al plus O2 would give me Al2O3. So that would give me, say, 2, let's say 2, and okay, that would be 3, and that would then be 4. Okay. Melting of ice is a physical process. Physical. Pulverizing panado tablet. Pulverizing means making it into a powder, so it's physical. Digesting an ice cream. Let's say ice cream has sugar in it, and that would be a chemical process, because you got carbohydrates and all that. What happens is you got that, and when it reacts with oxygen, it gives off carbon dioxide plus water plus energy, and the energy can be used to heat your body or to do mechanical work. So that is a chemical process. And then if we look at the explosion of nitroglycerin, we know that when nitroglycerin explodes, new substances are formed, and that would be a chemical process. And then boiling an egg, when you boil an egg, you denature the proteins, and that's a chemical process. A match burning, a match is like carbon, and it burns, and then it gives off CO2 plus energy, right? So we see that flame as energy that's being given off. So it's plus energy. Right, and then metal gets warmer, that's a physical process. Okay, see you next time.